Okay. Now, as we mentioned last time, in the laboratory, you frequently carry out the chemical reactions in water solution. And we talked about molarity and how you figured out how many moles and all that stuff. I would like to talk to you a little bit more about what happens to compounds when you dissolve them in water at the atomic level. Now, pure water, despite the fact that we think of tap water as pure water, it's not really. Pure water is distilled, has no gases, has no ions in it other than what come with water itself. Pure water does not conduct much electric current because there aren't any charged particles to move. This is a computer animation of the molecules in water under ordinary conditions, and all you see are molecules. Okay? And I don't want you to try this, but in distilled water, if you're sitting in the bathtub and your little brother or your little sister kicks the radio into the water because they'd rather have all their parents' attention than sharing with you, if you're sitting in distilled water, it shouldn't hurt you. But don't try that. Don't try it. Don't say Geanangel said to do it. Tap water, however, has enough ions in it to where if you drop the blow-drying apparatus machine into the water while you're sitting in there, it will kill you. Enough current can be conducted. But pure water, no. Now, we can use that idea in what's called an electrolysis apparatus. Sorry. Let's see if I can get this. I'm sorry. I even called it the wrong thing. It's a conductivity apparatus. It has a light bulb. It has in a circuit with the light bulb and a power source that comes in from the right here, a couple of metal electrodes. Now, when pure water is present in that beaker, and you plug in the cord to the power supply, the light bulb doesn't light. That's what saved you when your little sister dropped the hairdryer in there. Okay? No current is conducted. Now, if you had tap water or seawater or any kind of water that has dissolved ionic compounds in it, the light bulb's going to light. And that tells you that ions are present in solution because current flows by virtue of the fact that those ions can move between the electrodes, and they help conduct the current. If there aren't any ions, there won't be any current. So as water dissolves ionic compounds, the process results in the ionic compounds dissociating into ions. So if we put a crystal of sodium chloride in a beaker that had the light off, as it dissolved, it would make sodium ions, aquated here, AQ means aquated, and chloride ions, and the light bulb would begin to light. And as you put more salt in, it would eventually get bright. And the reason for this is, as I mentioned before, the positive ions will move toward the negative electrode, and the negative ions will move toward the positive electrode, and that conducts enough electricity to light the light. Now, let's see if we have, not sure whether you'll be able to hear this or not, but I'll show you conductivity apparatus here. Maybe.
If ions are present, a circuit will be completed that allows the current to flow. 4 different chemicals will be added to beakers containing distilled water, each time the solution is brought into contact with a conductivity device. A solution of sucrose, which is a non-electrolyte, is added.
I'll define electrolyte in a minute.
This solution contains no ions and does not conduct a current.
Light bulb doesn't light.
Between each demonstration, the electrodes are rinsed with distilled water to remove residual compound. A solution of acetic acid, which is a weak electrolyte, is added. This solution now contains only a few ions and conducts current weakly. Sodium chloride, a soluble salt and a strong electrolyte, is added. The amount of ions increases the conductivity, lighting the bulb.
Okay, I'm going to skip to the next slide. The rest of it is duplication. So I want to talk to you about solubility then of ionic compounds and the details of that process. So a substance, we saw sodium chloride. Potassium bromide would be a substance that acts very much like sodium chloride. That such a substance, when you dissolve it in water, if it conducts a current when dissolved in solution, it's called an electrolyte. Okay? Easy to remember. Light makes the light bulb light. Okay? Yes, go ahead. Oh, sorry. Thank you for telling me. Is that better? That's good. Thank you very much for telling me, reminding me. I knew, but I forgot. Okay. In the dissolution process, where KBr dissolves, the ions that are present in the ionic solid, K plus and Br minus, go into solution and form aquated ions. And for the KBr compound, 1 mole of the compound dissociates into 2 moles of ions. This process, of course, depends on the formula of the ionic compound. And you can determine how many moles of ions are produced by looking at the formula. For example, aluminum trichloride is an ionic compound that dissolves in water to produce Al3 plus, aqueous, and 3 chloride ions, aqueous. So this means you get 4 moles of ions for 1 mole of the electrolyte. Okay, so a little bit of that would really make the light bulb light. In addition to that, if we take something like ammonium sulfate, we know the ammonium ion and the sulfate ion, the latter having 2 negative charges, is going to require 2 of the former. And we will get 2 ammonium ions and 1 sulfate ion per mole of ammonium sulfate. So that'll be 3 moles of ion. And so all we have to do to determine how many moles of ions are in a solution is to look at the formula and know the number of moles of the compound whose formula we have. Okay? Then let's remember that soluble ionic compounds dissociate fully in solution, with very few exceptions. So here's a skill. Using the formula to find the number of moles of ions in solution, how many moles of each ion are in each solution? The first one is 5 moles of ammonium phosphate dissolved in water. Well, here's where your learning those ions back in Chapter 2 pays off, because they're not telling you what the formula is. You would have to figure that out if this were an exam question, which it probably is. So you would have to know the constitution of an ammonium ion and its charge and the phosphate ion as well. And then you would get the formula, and then you would use 5 moles of that formula to figure out how many moles of ions would be produced. Phosphate ion is PO4 with 3 negative charges. Ammonium ion has a single positive charge, so it will take 3 ammonium ions to balance the charge of phosphate. So if we dissolve ammonium phosphate in solution, it's a soluble ionic compound, so it dissolves completely. It dissolves, it's very soluble, and it dissociates completely into 3 ammonium ions and 1 phosphate ion, for a total of 4 ions per mole of the compound. Now, remember that unless there is oxidation reduction processes, unless there are oxidation reduction processes going on, you can assume that the polyatomic ions stay intact in the solution. So here's how we would determine the number of moles of ammonium ion. We take the number of moles of ammonium phosphate times the formula ratio, 3 moles of ammonium ion per 1 mole of ammonium phosphate, and that would tell us for 5 moles of ammonium phosphate, we get 15 moles of ammonium, and in addition to that, 5 moles of phosphate for a total number of moles of ions of 20 moles. Does anybody have a question about that one? All right, let's look at another one. 35 milliliters of 0.84 molar zinc chloride solution. Okay, we want to know, first of all, we want to know the number of moles of ions, so we're going to have to get the number of moles of zinc chloride to start with, and then we'll use the formula to get the ions. But we're given the volume in milliliters, and we're given the molarity. So in order to get the number of moles of zinc chloride, we'll take 35 milliliters, convert it to liters, 1 liter over 1,000 milliliters, times 0.84 moles of zinc chloride per 1 liter, and that gives us 2.9 times 10 to the negative 2 moles of zinc chloride. So then we take the formula, and we notice that the formula says there'll be 2 moles of chloride per 1 mole of zinc chloride. So if we take the number of moles of zinc chloride times the ion ratio from the formula, we find that we get 5.8 times 10 to the negative 2 moles of chloride ion, and half that much zinc ion. So that'll be 2.9 times 10 to the negative 2 moles of zinc ion. And if the question asks for the total number of moles, you would add those together. Questions on that one? Okay. Then, if not, the last one says 7.42 times 10 to the 22nd formulas of copper nitrate, copper 2 nitrate this is, dissolved in water. So here's copper 2 nitrate. You dissolve it in water. You get 1 copper 2 plus ion per mole, 1 mole of copper 2 plus per mole of compound, and 2 moles of nitrate ion per mole of compound. Now, we're given formulas, so we're going to have to think about converting the number of formulas of copper 2 nitrate to the number of moles, and then the number of moles of copper 2 nitrate to the number of moles of ions. So first, convert formula units to moles. 7.42 times 10 to the 22nd formula units times 1 mole divided by Avogadro's number gives us 0.123 mole of copper 2 nitrate. Then it becomes just like the other problem, 0.123 mole of copper nitrate, 2 moles of nitrate per 1 mole of copper nitrate, and that gives us 0.246 moles of nitrate ion, and half that much copper ion, according to the formula. So this only adds the conversion of the number of formulas to the moles of formulas. Questions on that? All right, so that looks pretty good. All right, let's do something a little different then. This is a workshop using molecular depictions to understand solution reactions. This is the beginning of one. We have two beakers here, and I'm not sure that you can see the ions. They're not exceedingly visible here. I'm not sure, so I'm going to write down what's in here. Inside beaker number A, I see 10 positive ions. And I see 1, 2, 3, 4, 5, 2 negative ions. And in beaker B, I see 1, 2, 3, 4, 5, 6, 7, 8 negative ions. And I see 1, 2, 3, 4 dipositive ions, dications. And the question says, which compounds are present in each beaker if these are the possibilities? A, KCl, Na2SO4, magnesium bromide, or silver nitrate. Now, if we look at the ones with plus ions, there's only 3 of them that have plus ions. So the possibilities are KCl, sodium sulfate, and silver nitrate. Those all have positive ions. Okay? And which ones of those have 2 negative, dinegative ions? Only one of them. So we can cross out the potassium chloride and the silver nitrate, and the compound in beaker A must be sodium sulfate. And incidentally, there are 5 formulas of it. We may use this later if I have time. So 5 formulas are present in that beaker. Later on, we may consider the question of what would happen if we pour the contents of this beaker into that beaker, but let's look at beaker B first. Beaker B has single negative ions, 8 of them, so that could be ammonium nitrate. It could be barium nitrate. Or it could be potassium fluoride. But then it also has 4 2+ ions, and ammonium ion is single positive charge, potassium ion is 2, so this has to be barium nitrate. I'm looking at the charges on the ions, and I'm assuming that you too know the charges on the ions because we assigned you to learn that in Chapter 2. Okay? If you don't know the charges on the ions, now might be a good time to go back and refresh your memory. Okay? So, how many formulas of barium nitrate are present in that beaker? B. 4 formulas. Okay, I will stop there, but later on, after we've talked about precipitation reactions, I will revisit this and we'll talk some more about it, assuming we have time. Okay? Any questions on what we did so far? All right. Now, water is able to do what it does because it is a very substantially unique molecule. There is nothing else quite like water. And we owe a lot of our way of life to the fact that we have a lot of water. If you don't think so, watch some of the movies that came back from Mars where there's a little water but not very much. Not a place I'd want to live, I think. Okay? So, water separates the ions in ionic compounds by overcoming their electrostatic attractions. Those ions in ionic compounds have strong electrostatic attractions, plus to minus, minus to plus. The ionizing power of water is due to the distribution of electrons in its bonds and to its shape. Now, whenever you have covalent bonds between different atoms, the electrons in the bonds will be shared unequally. Later on we'll talk about electronegativity, which you all remember about anyhow. The more electronegative atom, of course, will have the electrons in the bond spend more time close to it. But in any case, if the electronegativities are different, if the atoms are different, the electrons will spend more time on near one atom than the other. So in a water molecule, this is a space-filling depiction of the water molecule, and the black spots are the nuclei, and the orange spots are the electrons. The electrons spend more time closer to the oxygen atom, and since electrons are negative, that induces a partial negative charge, somewhere between 0 and 1 electron charge on the oxygen end of the water molecule, which is indicated by the orange coloring here. This leaves the hydrogens with less than a full ownership of these electrons. The electrons spend more of their time away from the hydrogen, and therefore the hydrogens have a relatively positive charge compared to what they were as hydrogen atoms. So what this means is the water molecule is quite polar. It has a north pole and a south pole. And these charged poles go together to make an overall charged molecule, as the colors on this thing indicate. Now, what I want to do is to show you the polar bonds in the water molecule by looking at what's called a polar arrow, which is just an arrow. It has an arrowhead that points towards the negative end of the bond, and it has a cross on the back of it which indicates which end of the bond is positive. So if we look at the water molecule, here's the oxygen, here's the two hydrogens, and the bonds are polar in the sense the electrons spend more time closer to the oxygen. So this arrow can be thought of as a vector. And in order to analyze the polarity of the molecule, you can do what you do in math class. You can take a vector and you can break it apart into its components, a vertical component and a horizontal component. And you can do the same thing for this vector over here. And what you'll find is the two horizontal vectors are of the same size, and they are pointed opposite to one another, so they're going to cancel. The horizontal vectors cancel. But what about the vertical vectors? The vertical vectors are going to reinforce one another. And so we're going to end up with a net vector up through the center of the molecule going from the hydrogen end through the oxygen and directly up. So that big arrow is why the water molecule as a whole is polar. So the combined effect of the polar bonds and the shape of the molecule makes water quite polar and allows it to attract ions strongly, both positive ions and negative ions. So if we just dropped a crystal of sodium chloride into some water, the water molecules would immediately congregate around the surface of that crystal. The surface of the crystal is made up of positive and negative ions, sodium ions and chloride ions. And I think if you imagine this, the water molecule will be attracted to the ions on the surface strongly, with its positive end, partially positive end, attracted to the negative ions, which you might see right there. And eventually, if enough water molecules crowd in around this negative ion, it'll be enough to rip the negative ion right out of the crystal, overcoming the attraction. And then if you see, the negative ion will then be out here in solution with a whole bunch of water molecules all around it. Okay, they've taken it hostage, I guess you might say. This is aquation process, AQ. This is what AQ means, and it's done in 3 dimensions. On the other hand, a positive ion is subject to attraction to the negative end of the water molecule, and as more and more water molecules crowd around, you will eventually get the positive ion ripped off and taken into solution and aquated. This is the dissolution process. This is fundamentally what happens when you put an electrolyte in water. Okay? So at the atomic level, water is overcoming the attraction of these ions for their neighboring ions at the surface. Now, if we think about an insoluble compound, you don't know about solubility, do you? We haven't got there yet. Well, I'll tell you, magnesium oxide is virtually insoluble. Water cannot dissolve it. And what that means is, in magnesium oxide, the ions are attracted to one another too strongly for water to overcome that attraction. And that has to do with the fact that in magnesium oxide, what are the charges on the ions? 2 plus on the magnesium and 2 minus, or negative 2 on the oxygen oxide ion. So water can't break those strong, high ionic charge attractions in the case of magnesium oxide. Okay, and what about other compounds besides ionic compounds? There are other compounds that dissolve in water. We know, right? Alcohol. Okay, if you drink an alcoholic beverage, it's a solution of alcohol in water, and there may be some other things in there. If you have iced tea and you like it with a teaspoon of sugar in it, you dump in the sugar and stir it up, and the sugar dissolves. Now, there are a number of different things that dissolve in water, but the properties of the solution are different than the properties of electrolyte solution. Ammonia is one, sucrose is sugar, ethanol, antifreeze for your car's radiator. Each of these molecules has one or more polar parts to it. This happens to be ethyl alcohol, CH3, CH2, OH. That is a polar bond right there, and it interacts strongly with the water molecule, and this allows the water molecule to disperse the ethanol molecules and form a homogeneous solution. But no ions are formed. So if we took this solution of ethanol and put it in the light bulb apparatus, nothing happens. No ions, no light. So these are polar molecules. They're soluble in water, but they're non-electrolytes because they don't form any ions. So that's what a non-electrolyte is. It doesn't like the light because there aren't any ions. Now there are yet some other materials, covalent materials, like benzene and octane and a few others I can think of, that also have non-polar molecules and don't dissolve in water. So these aren't electrolytes of any kind. They're insoluble. If you take some benzene, pour it into water, you get 2 layers. The benzene will be on top, and the water won't dissolve it. So that's not an electrolyte. It has to be soluble to be an electrolyte or a non-electrolyte. It has to be soluble in water. Now, another kind of covalent compound that's soluble in water is an acid. And you saw acetic acid in the little video. You saw her put the acetic acid into water and put it on the conductivity apparatus. And what happened to acetic acid? The light lit, but not very bright. Right? So there must be some ions. So acetic acid happens to be an acid that will dissolve in water. Almost all acids dissolve strongly in water. And it's a carboxylic acid. We learned what they look like. And when you put it in water, a small amount of it breaks up and forms the acetate ion. A few percent of the acetic acid molecules break up into ions. And these ions were enough to make that little bit of light that we saw. Okay? Not enough to make the light bright, but it showed that acetic acid is not a strong acid, or a strong acid would dissociate completely and the light bulb would be very bright. So acetic acid is a weak acid. Another weak acid is phosphoric acid, for example. Okay, now let's look at a problem that's based on these ideas. Sulfuric acid is a strong acid, and its formula is known to you as H2SO4, I'm sure. And being a strong acid, it means that the molecule undergoes dissociation when it's in water, and it produces, to a large extent, 2 hydrogens as ions and the sulfate ions. So if we wanted to find out what is the molarity of hydrogen ion in 1.4 molar sulfuric acid, we would do it from the formula and the idea that sulfuric acid is a strong electrolyte. 2 moles of H plus aqueous are formed for 1 mole of sulfuric acid. Sulfuric acid is such a strong acid that both of the H of the hydrogens that are present there dissociate in water. Now, we are making a little bit of an approximation here, as you'll see in Chem 2, but for all intents and purposes, in dilute solutions of sulfuric acid, the process of dissolving includes with it ionization, 2H plus SO4, 2 minus. So you get 2 hydrogen ions per formula of sulfuric acid, or 2 moles of hydrogen ion per 1 mole of sulfuric acid. So 1.4 molar sulfuric acid contains 2 times 1.4, or 2.8 molar H plus. Okay. Now the hydrogen ion is, of course, just a proton. But the fact that it has no electron means that the positive charge is concentrated on a very, very tiny nucleus. And if you look at the density of the positive charge, it's huge. It's enormous for this H plus. And H plus is so positively charged, so it has such dense positive charge that it cannot exist by itself in either liquid or solid. It can only do that in the gas phase under certain conditions. So hydrogen ion aqueous means that it is strongly attached chemically to water molecules. So the concentrated positive charge allows the H plus to strongly attract the negative pole. And you can write down this in various different ways. The usually simplest way is to let 1 H plus and 1 water be represented here. That'll give H3O plus, the hydronium ion. But actually, in aqueous solution, there's a good deal more interaction than that, because H3O plus interacts with other water molecules here and here, as you can see, and forms fairly strongly bonded ionic units here. So I want you to write down for me the formula of this ion. Okay? Can you do that? What is the formula of this ion? You see it has H3O plus, and there's 2 water molecules that are strongly connected electrostatically to it. Got it written down? So it's H3O plus H2O plus H2O. So it has 3 oxygens. It has 7 hydrogens. So it's H7O3. I'll put brackets around it since it's a complicated ion, plus. Okay, that's one representation of a proton in water. And in fact, they even get larger than that. And it's rather difficult to describe exactly how the hydrogen ion is interacting with the water in any given set of conditions that we might find. So what we typically do is we just represent the whole thing by H3O plus aqueous. And that way, everybody knows that we know that H3O plus is interacting with water in various ways.